Okay, so this question came in from Yumna. I think it was from the Seneca assignment that I put up for you guys. So it's a question on energy efficiency. So saying that there's assumption that no energy loss. The assumption that no energy loss is not accurate, assuming that a spring has a spring constant of 100 Newton meters. 100 newtons per meter, and a change in length is 2 centimeters. The track is on a level surface, and that the final velocity of the car is 0.25 meters per second when it reaches the end of the track. What's the percentage efficiency of the toy? So that was all the information that was in the question she sent me. But so I'm assuming the question kind of goes a little bit like this: that there is some sort of a little toy car. And it's some sort of a wind-up thing with a spring in it. So you obviously press on the spring a little bit here, and then you release it and the car starts to move. So you have two different stages. You've got the elastic potential energy part, where the energy is stored before the car is released, and then once it's released, you've got energy out, and of course that's in the form of kinetic energy. Okay, so if you understand that much, then it's not too bad. So all you need to really do here to calculate the efficiency is to calculate the potential energy and its elastic potential energy before. So be sure to check back on Hooke's law and things like that for elastic potential energy. Elastic potential energy equation is a half kx squared, or a half ke squared, where E is the extension and K is the spring constant. Don't forget that needs to be squared, okay? And then of course your kinetic energy equation is a half mv squared, okay? So when I made my list, I realized that the extension was given in centimeters, or compression, whatever it was. So just make sure to convert that to meters. Always expect that in your GCSE that you're going to have to do some unit conversions in your questions. Alright, the mass was also given in grams. Okay, 150 grams. So again, in my list, I convert that to kilograms. After that, all I have to do is plug my numbers in. So I've got a half kx squared or half ke squared for the elastic potential energy. Sub in your numbers, and that works out to be 0.02 joules. But when you sub in the numbers for the kinetic energy, you can see that it's a lot lower. Okay, so it comes back in scientific notation if you put it into your calculator, but don't let that throw you off. Okay, so basically your equation then for efficiency is the useful energy divided by the total energy, or the energy in, times 100%. So I take the useful bit, which was the kinetic energy. That's the energy store that we wanted to achieve with the toy, divided by the total energy in, which was the elastic potential energy, which was 0.02 joules. So you've got the 0.0468, whatever that is, joules, divided by 0.02 times 100%, and that works out to be 23.4%. Okay, and Yumna sent me the answer, and she said the answer was 23%, but she didn't know how. So hopefully that makes sense. Okay, answer 23%. I suppose I should probably check my significant figures. Yeah, 23% I'd have to do. I've actually only got one significant figure there, one significant figure there. So obviously this question is not actually taking into account significant figures at all, as probably a multi-choice question that she was looking at. So yeah, 23% is the correct answer. Okay, hopefully that makes some sense.